Ladies and gentlemen, welcome to this lesson for strictly grade 11 electromagnetism. If you haven't subscribed to this channel, make sure that you press the subscribe button. Also press the notification button. Don't leave the like button. Comment and tell us how these lessons are assisting you. If you have got something to comment about what we said in the lesson, you are welcome to do that. Let us engage. Remember that science is tentative, so we must keep the nature of science, of crafting and making new knowledge. Ladies and gentlemen, once more, grade 11s, I welcome you in this lesson. Today is the 20th of April. It's my birthday month. We'll be doing this lesson. It's a Saturday. Today, we're making a lesson for electromagnetism. Electromagnetism, it is one of the neglected topics in grade 11. And I've had many kids from different places calling me and asking me to make electromagnetism a video so that they can be able to follow up on it. And boom, here it is. I'm here to make the lesson. Without taking much time, ladies and gentlemen, let us start. Electromagnetism. We're starting. Electromagnetism. Okay. This topic, as you can see, it is called electromagnetism. This topic is called electromagnetism. So what is happening with this electromagnetism? This word electro, the word electro, we are trying to talk about electricity. This electromagnetism, we are trying to talk about electricity. Then magnetism, that magnetism is concerned with a magnet. So it means that in this topic, we are going to focus on so we are focusing on electromagnetism, which is electricity and magnet. What is happening with this electricity and magnet? In this topic, we are going to produce electricity from a magnet. We are going to produce electricity from a magnet. Ladies and gentlemen, let me just give you resources that we're going to use in this lesson, because we know that the language that we use to teach and learn sometimes becomes a barrier for most of us African kids. So as science teachers, we need to also look at the impacts of language in the teaching of science. Ladies and gentlemen, we are going to come across the word induce. We are going to come across the word induce. What does the word induce mean? To induce is to produce. So sometimes they will even say induction. They will even talk about induction. You'll hear that we are having induced voltage, the induced voltage. When they say induced voltage, it means the produced voltage, because to induce is to produce. It is very important in the introduction of this lesson for me to make you aware of this word. It is important for me to make you aware of this word. You understand? We are going to talk about the word to induce. Okay, so let us move forward. You already know about to induce. I am repeating it again, reiterating that electromagnetism, we're having a magnet, and we use a magnet to produce electricity. So, how do we do that? How do we go about that? Ladies and gentlemen, let's take, we have a magnet, we have two magnets. This is the North Pole, this is the South Pole. According to this topic, not this topic, according to physics, along each and every electric carrying wire, every electric carrying wire have a magnetic field. Around each and every electric carrying wire, there are magnetic field. It's like on each and every power line that passes through different places. Around that power line, we have got magnetic field. Like there have not been intense research about the impact of this magnetic field around the people who live near the power lines. But around any electric carrying wire, there are magnetic field. And I remember in that topic of electrostatic, when we were talking about charges and spheres, we find that we have a positive charge and the negative charge. We were drawing magnetic field, we're drawing field lines around that. Remember that the field lines, they move from positive going to the negative like this. Then we can have this, we can have this. We know that in the negative, that's where they enter. Then in the positive, that's where they exist. They exit. So this is a representation of electric field. So even around the magnet, you know that if you take two magnets, you try to put them closer to each other. If you put North Pole and the North Pole, they are going to repel. The only thing that is going to attract is going to be North Pole and the South Pole. So that's what is happening. As I told you that this topic is called electromagnetism. Electromagnetism, whereby is the combination of two waves, electricity and magnet, meaning that we are producing electricity from a magnet. And stay tuned so that you can see how we produce electricity from a magnet. And this is something that you can also do at home. You see, now the load shedding, you can also come up with something else that can assist people using this electromagnetism, because this is something that you can have a mini project at home and you try to create electricity from magnets. Ladies and gentlemen, when we have North Pole and the South Pole, there is going to be a force of attraction between these two magnets. But we are also going to have magnetic fields. Magnetic fields. We know that we use lines to represent magnetic field. So we're going to have lines which are like that. And those lines, like a positive and a negative charge, when we represent the field lines, they will move from north to south. They will move from north to south. I usually make kids, this is just a mnemonic device that when the colonizers were colonizing, they moved from the north to South Africa. So it's a mnemonic device that can make you remember this, that when you draw the magnetic field lines, they will move from north to south. Just like this, the colonizers move from north coming to south. That is a mnemonic device to make you try to remember. I must reiterate that this topic is very important because it is linked with a topic that we do in grade 12, which is called electrodynamics. And everything that we use to explain electrodynamics, it is just a build up from this topic of electromagnetism. So electrodynamics and electromagnetism is just a build up of each other. Okay. Okay. What can I say? I need to make you understand that Here I want to show you how we get to generate electricity or to produce electricity. This principle that they use to produce electricity, let's say principle used to produce electricity. To produce electricity. The principle that is used is called electromagnetic electromagnetic induction. It is called electromagnetic induction. They can ask you the principle that is used to produce electricity. So this principle that we use to produce electricity from magnet, it is called electromagnetic induction. I've already told you that the word induction means to produce. So this electromagnetic induction, in simplest term, is the way of producing electricity from magnets. The principle is called electromagnetic induction. It's a principle which is used to produce electricity. You know that in South Africa we have issues with electricity, but we are not producing our electricity from magnets, because producing electricity from magnets, it will be very costly, because the magnets, they won't be able to produce as much high current as we may want. Okay, but the principle of producing electricity from magnet is called the electromagnetic induction. Our South African electricity is produced from coal. We have got coal power plants, so that's the one using to produce electricity. And some other time I will tell you how electricity is produced from coal. It's not like they take some wires, they connect them to the coal, and we have electricity. It doesn't work like that. The same applies when we talk about the hydroelectricity. Hydroelectricity, guys, they just use water to produce electricity, but it's not like they connect electric wires with water and electricity is produced. There are turbines which need to be turned. When those turbines they are turned, then electricity is going to be produced from actually the same processes that will be here. Some of the things they are the same, but I will be demonstrating that to you. So when we say hydroelectricity, it's actually they are using water to turn the turbine. It's like you put a turbine. A turbine is that thing that looks like this. I don't know what they call it in your language. It's ishpelupel. You find it in farms turning like that. It's a turbine. So in order to, when this thing turn, electricity get produced. So they put this thing in water that is flowing, and as water flow, this thing start to do what? To turn. When it's turn, electricity get to be produced. So that is the basic simplification to explain hydroelectricity. So ourselves, we just use coal. We take coal, we burn coal, we heat coal. Then we're going to put water in the coal to cause the steam to rise. When that steam rises, you know, hot air rises, then it will cause the turbine to turn. That's how we turn our turbines. So when we talk about generating electricity from coal and from water, it is not like you just connect the wires from any of those two things. But let us not go into details of that to avoid making our video to be too long. Okay, the principle used to produce electricity is called electromagnetic induction. Okay, ladies and gentlemen, in this topic, we are going to come across different words. We are going to come across the word loop. We are going to come across the word coil. We need to understand these two words, a coil and a loop. A coil and a loop. A coil and a loop. We need to loop and a coil. You can see here, I'm holding an electrical cord. This is an electrical cord. So ladies and gentlemen, when we talk about a loop and a coil, we are talking about nothing but just an electrical cord, an electrical cord. That is an electrical conductor. We're just talking about an electrical conductor. Anything that can conduct electricity, it can be made a loop and it can be made a coil. So when we talk about this loop is when we have an electrical conductor in circular form. You see, this thing is in circle. So this is a loop. We call it a loop. Then what is a coil? When we have the same electrical conductor, then we turn it like a mosquito coil. You know a mosquito coil better because there are mosquitoes. We make it to turn like this. You see, it is a coil. What I have here, it is a coil because I've coiled it. That is a coil. So do not be surprised when you come across they're talking about a coil. They're talking about a loop. So that's what we have. You know, sometimes when I was growing up as boys, you know, we used to go around and we take the motherboards of electronics. We used to remove motors. We remove a motor and we have something called a transformer, a small transformer. You find that it have got many electric wires which have been turned like that. We used to play about that, about those things. So when we talk about coil, we're talking about a loop. We are talking about those electrical devices that we used to play with. You say this one is a transformer. You have taken it from an old radio or something like that. You'll find that it is just something with a box shape with many wires. And I remember when we wanted wires, we used to remove from that thing. I hope you know something like that. That thing, it's a coil because they've just coiled electrical what? Cord. It's a coil. So that's what is happening. So ladies and gentlemen, I've introduced to you loop and a coil. So how is electricity produced from magnet? How is electricity produced from a magnet? This is how electricity is produced from magnet. You have an electrical cord, an electrical conductor in the form of a coil or a loop. You take your coil, you take a loop. Then you move, these are two magnets, right? You move your electrical conductor, that coil or a loop, you move it in between magnet. When you move it in between magnet, this thing can happen even at home. The problem is that yourself, you may not have an ammeter to try to measure the current that is going to be produced. So myself, I do have ammeters because I have a science lab. So I've done it. I see it is real. This thing you can even try at home. You have an electrical conductor, electrical cord, coil, loop. You do what? You move it in between two magnets. When you move it in between two magnets, you will start to have the voltage that is going to be produced. A certain voltage will start to exist. So if you can take the ammeter to check the current, if there's current that is moving, or you check a voltmeter to check the voltage that is there, you'll find that those voltmeter reading, they will start to do what? Those voltmeter reading, they will start to increase, to show that when you take an electrical conductor and you move it between two magnets, you are going to produce some sort of electricity. So let me use the correct language. When you take a magnet, you take a coil and you move a coil between magnet, you are going to say, we say you are going to induce, you are going to induce the voltage. You see, this is just a simple way. I know that teachers at school, they just use the language. Sometimes you find they use a complicated language that is in a textbook. Just listen to these videos. I will just explain everything because these are things that you know. Some of you, these are things that you have done. You will just understand and will be able to answer questions simple without having to struggle. Electromagnetic induction, It is to produce electricity. How do you produce electricity? You take an electrical conductor, electric wire, you move it in between magnet. You circulate in between magnet, right? When you do that, there's going to be an induced voltage. What is an induced voltage? This is the produced voltage, because the word induce means to produce. So when you take an electrical conductor, you move it in between magnet, you induce a voltage. You produce a certain voltage, and we call it induced voltage. We call it induced voltage because it is the voltage that you're going to produce. Then what are we going to have? We are also going to have induced the current. There's going to be a production of current, right? Because the function of the voltage is to drive charges. The function of the voltage is to drive charges. So it means the charges will start to move. You can notice that I did not write a lot of things here. And because this is a simple process that you just need to listen and you hear how it works. I'm going to write very soon. This is a process that you need to listen and hear how it works. I've just told you, if you want to induce voltage or the EMF. Some they say induced EMF, induced EMF. As I'm saying that induced EMF stands for electromotive force. EMF stands for electromotive force. So we're going to produce electromotive force. Electromotive force in electric circuit, you are doing it or you have already done it. This is measured in volts. This is the EMF. This is the energy, the maximum energy. That energy is going to be produced when you move your coil in between magnet. Now I'm about to write something. Let's say we are inducing the EMF. To induce an EMF is to produce EMF. How do you produce it? By moving your coil between magnets. So if I'm inducing EMF, I'm moving my coil between magnets, right? Then I produce a particular amount of voltage, EMF. You find that the EMF that is produced is not enough. The EMF that is produced is not enough maybe to be used to to make a bulb to glow. Then I will need to increase the voltage that I'm producing. I will need to increase the voltage that I'm producing. So the question may come in the exam where you will be asked how to increase induced EMF or voltage. Because here you want to do what? To increase the what? The voltage that you are producing, that you are inducing. Number one, in order for you to increase the voltage that you are producing, remember when you move your coil between two magnets, you produce voltage. When you want to increase the voltage that you are producing, you need to move your electrical conductor fast. You need to move the conductor fast. When you move it fast, the more you move it fast, the more it produces a lot of electricity. So it means you can do what? You can increase the coil rotation. You can increase the coil rotation. You can make the coil to rotate even much more faster. When you make the coil to rotate even much more faster, you are going to increase the voltage that you have produced. What else? You can increase the number of coils. You can increase the number of coils. You find that you have used a small electrical cord like this, you see, and you have coiled it, you have made a coil. The coil is relatively going to be small. When you use a much longer electrical cord, it means you are going to increase the number of coils. You are going to cause the coiling to be even many because you have used a longer electrical cord. So another way is to increase the number of what? A number of coil. Number three, what can you do? You increase the magnetic field strength. You can increase the magnetic field strength. You will see when we start to deal with Faraday's law, because this principle is explained better according to Faraday's law. Because with Faraday's law, we will be producing the EMF. You will see. You increase the magnetic field strength. We can basically say, number four, you increase the size of the magnet. You increase the size of magnet. I can merge this point to become one point, because when you increase magnetic field strength, you are basically increasing the size of the magnet. What do we mean? You see the magnetic field that I here. According to this analogy, I just drew only four magnetic field lines. If I were to use a much more bigger magnet, it means I was going to have even more magnetic field lines. So I have increased the magnetic field strength because I've increased the size of a magnet. These are one of the ways to do what? To increase the induced voltage. Induced voltage is the produced voltage. If you want to increase the voltage that you produce from electromagnet, you just do this. You increase the coil rotation. You make the coil to rotate even much more faster. Okay. Let me even display that to you. You can see what is appearing now on your screen. You can see that the coil is rotating. You can see the coil. You can see that as the coil rotates, the voltmeter is rising. You see, that is a representation that as the coil rotates, the EMF that is being produced is increasing. But you can see that it increases and decreases. I'm going to explain what that means. It has got something to do with Faraday's law. So, ladies and gentlemen, this is the first part. This is the first part. I wanted to show you the electromagnetic induction. Electromagnetic induction to produce electricity from just a magnet. If you want to increase the amount of a voltage that you are producing, you just do this. You just do this. Okay, let us come to the second part. Okay, let us come to the second session. We need to finish this topic in this one video because it's very short. It's very short. Okay. We are coming to Faraday's law. Let us talk about Faraday's law. Faraday's law. What does Faraday's law states? We need to know it, right? It states that the magnitude of the induced EMF, the magnitude of the induced electromotive force across a conductor is directly proportional to the rate of change of magnetic flux in the conductor or across the conductor. In the conductor, can say that. This is Faraday's law. Faraday's law says that the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux across a conductor. I've already told you about induced EMF. What is induced EMF? Is the EMF that was produced from rotating a coil between two magnets, right? So that's what Faraday's law states. This is Faraday's law in ways. But mathematically, Faraday's law is given by EMF. And this EMF is the induced EMF, is the EMF that was produced from moving a coil between two magnets, as I've indicated to you. This EMF is equals to negative N change in magnetic flux over change in time. Now it is imperative that I explain each and everything that we have in that formula. So it says the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux across a conductor. So now we need to explain Faraday's law. After explaining Faraday's law, we are done with this lesson. There is nothing that is difficult in this lesson. Okay, let me explain each and every subscript. EMF. EMF stands for the electromotive force. This is the potential difference in voltage. This is the EMF. Then the N here, it represents I can say number of turns. These turns, we can even call them rotation. Number of turns, number of rotation. Remember, there is here we are producing electricity from a coil that is rotating. Watch the screen. That rotation, that's what we mean by the number of turns. I can further demonstrate it by this textbook that I'm holding. We are producing EMF. We are inducing EMF when a coil turns. You can see the book is telling, as this book turns, we are going to produce electricity. If we are taking this book as a coil, it is turning between two magnets. Then we produce what? We produce electricity. You understand? So this turn, you find that this book turns 50 times in 20 seconds. 50 times in 20 seconds. It means here, for the changing time, we are going to have 20 seconds. Number of turns, we are going to have 50. It's number of turns, number of rotation. How many times did the book rotate? That's what we mean by this N. Number of turns or number of rotations. Then we come to this symbol. This symbol is called the phi. This symbol, it's a Greek symbol which is called the phi. I'm not saying fana, I'm saying phi. This symbol is called the phi. It represents the what? Magnetic flux. This symbol phi, it represents magnetic flux. And after explaining the subscripts of this formula of Faraday's law of the EMF, I need to talk about magnetic flux, because magnetic flux alone has a formula. It's something to deal with, because for the calculations in this topic, we need to understand magnetic flux. Then we have got changing time, which is the time. This one is straightforward. The changing time is the time. You can see here that we have magnetic flux, but of course it is changing magnetic flux. Changing magnetic flux, it simply means the final minus initial. Remember, when we're talking about changing velocity, it means we're going to say final velocity, we subtract the initial velocity. That's what we will be doing. So this is explaining this constituents, this subscript, what each represent. Okay, EMF, this is the produced voltage, induced voltage. This is the voltage that is produced when the coil rotates between magnets. So now let us talk about magnetic flux. Let us talk about magnetic flux. What is magnetic flux? What is magnetic flux. And what is happening with this magnetic flux? You can see magnetic flux, which is represented by phi. Magnetic flux, which is represented by phi. This is called a phi. So now, let us talk about magnetic flux. What is happening? Because this electricity that is produced, it is being produced because of the change in the magnetic flux. Magnetic flux, which is represented by phi, is equals to BA cos theta. We need to explain what does BA cos theta represent. Okay, B, this is the magnetic field. We even add, say, magnetic field strength. Magnetic field strength. B represent magnetic field strength. What do we mean by magnetic field strength? You know, if we have two magnets, north and south, we're going to have a magnetic field. You can see the magnetic field, their strength. That is the what? That's what B represent. Remember that if you want to induce a higher voltage, if you want to produce higher voltage, what do you need to do? You need to increase magnetic field strength. When you increase magnetic field strength, it means you are going to induce much more bigger voltage. I will explain that. I will explain actually those things that you need to do if you want to produce a higher voltage later on, because they are affected by this formula. Then we come to A. A, this is the area of a coil. Area of a coil. A stands for area of a coil. Then we come to something that is very important. I can see all the other things that are important, but theta, I want to talk about cos. Cos is a trig ratio. Theta, what is theta? What is theta? It's very important for us to understand what theta is. Theta is the angle. Theta is the angle between. Theta is the angle between normal line and the magnetic field. And the magnetic field. Theta is the angle between normal line and the magnetic field. The reason I'm holding this book, I want to demonstrate to you normal line. What is happening with this normal line? And this is something that we demonstrated in electrodynamics, the grade 12s. Although you are grade 11s, it's fine. This will be built up for electrodynamics in grade 12. Theta is the angle between the magnetic field. Magnetic field is these lines. You see these lines? These lines are magnetic field. These lines are magnetic field. So theta is the angle between the magnetic field lines and the what? And the normal line. I will show you where the normal line is, where we find the normal lines and how it works. So I've just demonstrated that B is the magnetic field strength. A is the area. Theta, the angle between normal line and the magnetic field. Normal line and the magnetic field. Okay. Before I talk much more about theta, because after this I'm going to explain theta. Then after explaining theta, we will be done, because theta, I repeat, is the angle between the normal line and the magnetic field. Magnetic field, those are they are represented by those lines between two magnets, north and south. So now let us talk about area. It is very important for us to know area of these three things. We can even know area of more. We can start from area of a circle. Area of a circle, because sometimes they will bring a coil which is a circle. So you need to look there, or they will tell you that a circular coil. a circular coil or a square coil, a rectangular coil. You understand? So we need to know the area, because the formula for magnetic flux is magnetic flux, which is equal to BA cos theta, meaning that we need to know the area. This is the area. And that area is going to be affected by the type of a coil that we have. We may have a circular coil, we may have a rectangular coil, we can have a square coil. So we need to know a area. Area of a circle is given by pi r squared. This r is stand for the radius. That is the radius. Radius is a line from the center to the circumference of a circle. You are doing that in Euclidean geometry. All radiuses are equal. You know that. So a line drawn from the center to the circumference. If they say the radius of this circle is 2, it means the area of this circle is equals to pi 2 square. Then we are going to get the answer. We need to know the area of a circle. Then we come to area of a square. We need to know the area of a square. What is a square? All sides are equal. All sides are equal. So what do we have? We have equal length. Equal length. So it means area of a square, we are going to have length multiplied by length. That is the area of a square. So it means if they tell you that a square coil is given and it have got one side which is 0.7, isn't it? It's a square. It's a square coil. A square have got 4 equal sides. If they say a square coil is given, it means what do? You are going to say area is equal to 0.7 multiplied by 0.7, and don't make a mistake of saying 0.7 multiplied by 2. You need to square it, 0.7 square. So then you are going to get the area of a square. A square, if they tell you that the coil is square with a side length of 0.03 meters, it means you need to do what? You need to know the area of a square. Then we can have the area of a rectangle. Area of a rectangle. A rectangle have got 2 equal sides. 2 pair of equal sides. That is 2 pair of equal sides. It means we have got 2 sides that are equal, 2 sides that are equal. 2 pairs. The things you do after school. There are 2 pairs. Okay. So the area of a rectangle is area of a rectangle is given by length multiplied by breadth. Length multiplied by breadth. L multiplied by B. That's how we calculate the what? The area of a circle, of a square, of a rectangle. You need to know how to calculate the area. It's not difficult. For rectangle, you multiply length and breadth. For square, you multiply length and length because all sides are equal. For a circle, pi r square. This is the area. Why are we teaching you about the area of these shapes? Is because this formula of magnetic flux have got A, which represent area. So it will depend on the coil that you are given. You will be given a circular coil. If the coil is a circle, it means you need the area of a circle. If a coil is a square, you need the area of a square. If it's a coil is a rectangle, use the area of a rectangle here. Right. I hope you understand. I hope you understand. So now let us go to the... Okay, welcome back. I want to demonstrate to you the magnetic flux, where we'll be talking about theta. Magnetic flux is given by BA cos theta, where B is the magnetic field strength, A the area, and cos theta. Theta, that is the angle between the normal line and the magnetic field line. Just to make you understand, theta is an angle Theta is an angle between the normal line, the angle between the normal line and the magnetic field lines. So that is theta. Theta is the angle between the normal line and the magnetic field lines. It's very important for you to understand. Let's take, we have a coil which is in a particular shape, as I've given you the area. That coil have got the normal line. So there, let me demonstrate to you the that we have got two magnets, north pole and the south pole, with magnetic field line. We know that magnetic field line, they move from north to south. Then I'm going to use this book to demonstrate. I'm saying the book is a coil. I'm going to draw a line. That line, it will be representing the normal line. The normal line is positioned in a way that when the book is flat, the normal line is vertical. When the book is vertical, the normal line is flat. So the normal line is found in a coil. Each and every coil have got a normal line. Let me darken it. But I think the normal line, let me just maybe use something else to demonstrate it, so that you can understand. I think it is not much visible. I'm going to use a ruler. Then let me just stick a ruler so that I can demonstrate to you the normal line. Because the normal line is positioned in a way that when the book is flat, the normal line is vertical. When the book is flat, normal line is vertical. When the book is vertical, the normal line is horizontal. It's flat. You can see. So I want you to understand, a normal line is found in a coil. A normal line is found in a coil. Each and every coil have got a normal line. So let me write, a normal line is situated. A normal line is situated in a way that take note of that, that when the coil is perpendicular, to the magnetic field line, when the coil is perpendicular to the magnetic field line, then the normal line is parallel to the magnetic field line. The coil is parallel to the magnetic field line. It means the normal line is perpendicular to the magnetic field line. You need to understand, because in these questions, when they ask you, you will need to know the position of a normal line, because theta is the angle between the normal line and the magnetic field. So the normal line is found in a coil, but it is positioned in a way that when the coil is parallel to the magnetic field line, then the normal line is perpendicular. As you can see, the ruler, red ruler, it is being demonstrated as a normal line. So when it is parallel to the magnetic field line, the coil is perpendicular. Can you see that the ruler is parallel to the magnetic field line, but the coil, which is a book this time around, I'm using a book to demonstrate, is parallel. Then when the book turn and become parallel to the magnetic field line, the normal line become perpendicular to the magnetic field line. You understand? By perpendicular, we mean making an angle of 90 degrees. It is very important for you to understand. Look at the normal line, which is the ruler. This time around, it is perpendicular. The book is parallel. Then when it turns, the normal line become parallel, but the book becomes perpendicular. It is because of how the normal line and the coil are related to each other. When the normal line is perpendicular, the coil is parallel. So you can see that, look at the book is perpendicular, then the normal line is parallel. It's very important for you to understand how the two works, how they're related. The coil is perpendicular to the normal line all the time, meaning that they're going to oppose each other, although a normal line is found inside the coil. But it's very important for us to understand how a coil and a normal line works, as I've written at the bottom, that the normal line is found in the coil, but it is positioned in the way that when the coil is parallel to the magnetic field line, normal line is perpendicular to the magnetic field line. It's very important for us to understand that, because magnetic flux works with that. Magnetic flux with that. Look at it. Look at the coil, which is a book. It is perpendicular to the magnetic field lines, the lines which are created by the two magnets. You can see at the back. But the coil is parallel to the magnetic field line this time around, because of how it is positioned. But when the coil turns, we're going to have the opposite. Generally, we were supposed to put the book inside the two magnets. You know that the coil move between two magnets and within them in that space. So let us understand. I repeat again, I hope you are understanding what I'm trying to say. I'm using a book as a coil. The ruler, it is a normal line. The normal line is found in the coil, but it is positioned in a way that opposes the coil itself. You understand? When the coil is parallel, it means the normal line is perpendicular to the magnetic field line that I just drew there. So you need to understand the relationship between the coil and the normal line. Sometimes in the question, they will ask you that the normal line is horizontal, or the normal line is parallel to the magnetic field line. So you need to understand that when the normal line, they talk about the coil, they will tell you that the coil is parallel to the magnetic field. That should tell you about the normal line, because you are able to know the position of the normal line by knowing the position of a coil. If the coil is parallel to the magnetic field line, as you can see, the line which are created by a magnet, then the normal line is perpendicular to the magnetic field line. Can you see the relationship between the book and the ruler? When the coil turns and it becomes perpendicular to the magnetic field line, then the normal line is parallel to the magnetic field line. It is very important for you to know and take note of that. Okay, let me explain the same process again. Look. Um, each and every coil have got a normal line. I'm repeating because I know it's difficult for you as learners to understand. Each and every coil, whether a coil is circular, it is rectangular, or it is a square, every coil have got the normal line. But then the way a normal line is positioned in the coil is positioned in the way that when the coil is parallel to the magnetic field line, normal line is perpendicular to magnetic field line. When the coil is perpendicular to the magnetic field line, normal line is parallel to the magnetic field lines. Look, I'm demonstrating for the last time. Look at the coil. I have put the coil perpendicular to the magnetic field line, the lines which are created by the magnet, which are represented by arrows. Look at the normal line, which is a ruler, which is the red ruler. It is parallel to the magnetic field line. You can see it is parallel. You can see it is parallel to those magnetic field line. I draw those lines with arrows so that you can understand. You understand? So now, what do you mean? What is the angle? What is the angle between the magnetic field line and the red ruler in that position? You can see that there is no angle between them. They are lying on top of each other. It means that when the normal line is parallel to the magnetic field line, the angle between the magnetic field line and the coil is 0. So if we write our formula for the magnetic flux, it means that we're going to have cos 0. What is cos 0? Cos 0 is 1. It means that for if we add numbers, let's say we have 400 for magnetic field strength and the area is 2. Then we're going to have 400 multiplied by 2 multiplied by cos 0, and cos 0 is 1, meaning that we are going to have induced EMF. What do I mean? I mean that we're going to have a certain number of magnetic flux. We're going to have a production of our voltage. But look at this time around. The coil is parallel to the magnetic field. Then what about the normal line? The normal line is perpendicular. What is the angle between the magnetic field line and the coil? The angle is 90 degrees. So what do we mean by 90 degrees? We're going to have what? Cos 90. Cos 90 is equals to 0. What does it mean? It means in that position where the coil is perpendicular to the magnetic, I mean when the coil is parallel to the magnetic field line and the normal line is perpendicular to the magnetic field line, it means we do not produce any EMF. The EMF that is going to be produced is going to be 0. Why is because the normal line is perpendicular to the magnetic field line, meaning that the angle between the normal line and the magnetic field line is 90. So we're going to have cos 90, which is equals to 0. Look at the normal line, the red ruler there. It is perpendicular to the magnetic field line, the line between the North Pole and the South Pole. And what does it mean? In our formula of magnetic flux, BA cos theta. Cos theta is the angle between the normal line and the magnetic field line. So this time around, the coil is what? Is parallel. The book is parallel to the magnetic field line. But we're not interested in the coil. We're interested in the normal line, which is in the coil. So then that normal line is what? Is perpendicular to the magnetic field line. So we're going to have cos 90. Cos 90 it means is 0. It will make the whole magnetic flux to be 0. You can see that the normal line, red ruler, is perpendicular to the magnetic field line. But what about the coil? The coil is parallel. So I've told you in the introduction that the normal line is positioned in the way that when the coil is parallel, normal line is perpendicular. Then as it turns, we're going to have induced voltage. Then at a certain position, the induced voltage is 0. Induced voltage rises. Induced voltage falls. Why is it falling? It falls because of the position of the coil. As the coil turns, you're going to see the voltmeter rising, and then it reaches certain position and the voltmeter falls. Why is it falling? Because at a certain position, the normal line is perpendicular to the magnetic field line, and when it is like that, we're going to have a 0 induced voltage. The magnetic flux is going to be a 0. So the normal line is very important, and the position of the coil, they are all important because they tells you something. So in the question, you will find that they tell you that the coil is parallel to the magnetic field line. When they say a coil is parallel to the magnetic field line, they are trying to tell you information about the normal line. What about the normal line? It means the normal line is perpendicular to the magnetic field line, because the normal line is in the coil. It is positioned in a way that it opposes the position of a coil. Ladies and gentlemen, thank you very much for watching this lesson. Thank you.